given 0 to 2, 0 to the square root of 4 minus x, and you're integrating some function by dy dx. The question is to rewrite the integral so that it's in the form of dx dy. How do you do that? Well, first you have to draw the domain. That's the first step. Question. Change the integral. Change the order of integration. Integration. And we're trying to go from dy dx to dx dy. That's what it means. Solution. First of all, if you have dy here, you should really think of this here as y equal to 0 and y equal to square root of 4 minus x. And this should be thought as curve to curve. So you're really trying to draw this graph and draw this graph on the two-dimensional plane. Let's try that. Y equals to square root of 4 minus x. What is the graph of this? Well, now some of you may remember that y equals to square root of x is like this, right? So 4 minus x, 4 is going to shift this in some direction, and minus is going to change the way it's going. So instead of this way, it's going to go that way. It's minus is some type of a reflection. So if you can figure out what kind of transformation is applied, and if you can draw it, that's wonderful. But if you didn't, it's still okay because you can just make a table, right? So let's plot a few values, x and y. So if x is 0, y is 2. If x is, let's see, what's the next good number? If I plug in 1, see, plugging in 1 doesn't do much because you get 4 minus 1, which is 3 square root of 3. I don't know what that is. So let's move on to 3 because I like 3 since 4 minus 3 gives you 1 and square root of 1 is 1. And then if I plug in 4 you get 0. So I don't even care about this. It's just 0, 2, 3, 1, 4, 0. Let's just try to plot those points and see what kind of graph I get. So 0, 2 is 1, 2 right here. And 3, 1 is 1, 2, 3, 1. And then 4 is right here. And we're trying to come up with a curve that's like this. And since we know that this should be something similar to y equal to square root of x, which was like this, we see that it must be something like this. So that's the graph. Okay? That's the graph. Now, then y equal to 0. What's y equal to 0 as a curve, as a graph? Y equal to 0 is a horizontal line, right? Y equal to 0 is a horizontal line, which is the x-axis itself. This is y equal to 0. Therefore, when you read this, you should really think of it as starting from here, and you go up until this curve. So you begin here and you end there. That's what from here to there means. Okay. And then you have the x values. Now this is from point to point. These are just values, the limits for the x's. So x equal to 0 and x equal to 2 are the limitations. So x equals to 0 is right here. X equal to 0 is right here. X equal to 0. And right here, this is x equal to 2. And what you're trying to do is, because dy is inside, you're trying to cover a region going upwards. That's what dy means. And your leftmost point that x can have is 0, so you go here, until you reach the right end point, which is x equal to 2. So this is the domain that you get. start from the bottom curve, you end at the top curve, and there's the limits for the x value in, left and right, going upwards, covering this region. Alright, now let's try to represent this domain using dx dy. Now the thing that you're integrating doesn't change, but what you're trying to do is you're trying to cover this region with respect to dx. dx being inside means you're trying to cover the region as you're going right. You're trying to paint this as you're going right. And you have to write an equation here and write the equation there that describes the left curve and also the right curve. Now when you try to do this, you realize that there's something going on right here, because if you look at it, this is a straight line going down, right? Whereas above this point, it's a curve. So there's something happening above this dotted line and below this dotted line. Below this dotted line is just it starts at this straight line and ends at straight line. Right? As you're going right, you start from this curve and you end up at this curve, right? So below that dotted line, it's rather easy to describe what's happening. You start at x equal to 0 and you end at x equal to 2. However, if you're above the dotted line, you still start at x equal to 0, but you start at some point on this curve. You start at this line and you end at that curve. So you realize that when you try to paint this region going rightward, you can't simply use one single integral to represent the domain. And therefore, you have to incorporate two integrals rather than one. Okay? So, and sometimes this happens. When you go from dy dx to dx dy, sometimes you may end up having to use one or two, or maybe even three different integrals just to represent the same domain. Okay? All right, so let's try it. So if you realize that this is not this is equal to, if you write an integral that's equal to the previous one, you can't do it with just a single integral. You actually need two. And let's do this easier one first. The box one, the rectangular one. Okay. You start at x equal to 0 and you end at x equal to 2. So you start at x equal to 0, you end at x equal to 2. Now for this rectangle, what's the minimum value of y and what's the maximum value of y? 0 to where? How would we know this? Well, if I plug in 2 to this graph, remember this is the graph, right? If I plug in x equals to 2, I get y equal to square root of 2. So what's the coordinate of this point? This point has the coordinate 2 comma what? Square root of 2. If I plug in 2, I get square root of 2. So that's the coordinate of this point. And since this dotted line is passing through 2 comma right equal 2, the maximum value of y is square root of 2. Yes, exactly. So from y goes from 0 to square root of 2. On the other hand, if you want to represent this small region here, you first have to rewrite this in terms of x, because see, when you have dx here, that means you're trying to represent everything as x equal to something, x equal to something. This is easy. It's still, you start from 0, but that doesn't change. But now, my goal is to represent this top curve in terms of x equals to something. How do you do that? How do you describe this curve as x equals to something? Yes?
Solve y divided by 4.
Yes. You take this, because this is representing this curve here, you want to take this and solve for x, and that will give you the description in terms of x equal to something. So let's do that. So I have y equal to square root of 4 minus x, square both sides, you get y squared equal to 4 minus x. And then, let's see, add x both sides to get y squared plus x equal to 4. And finally, x is equal to 4 minus y squared by subtracting y squared both sides. And therefore, I figured out that x equal to 4 minus y squared describes this curve. So that's what I'm going to do. 4 minus y squared. Okay. And what we're getting is x starts from here and x ends here. That's what this is. X equal to 0 is that line on the left side. This is that curve on the right side. So you start from here and you end there. All right, for that, what's the minimum value of y? Yes. Radical 2, because that's where this point is. So you start at this dotted line. So minimum value of y is radical 2. What's the maximum value of y?
2. 1.
2. It goes up until 2. See, this point right here is what? 0, 2. This coordinate is 0, 2. So the y value has the maximum of 2. And that's it. You've succeeded in representing the original integral of which was in dy dx into an integral that's in dx dy, and we found out that we actually needed 2 integrals to achieve it. Sometimes that does it.